Hello there, welcome to our first data preprocessing video. Today's topic will be outlier detection, the proximity-based method. In order to do that, we will need to talk and use a lot of other concepts related to statistics, algorithmic, and data science. But you don't need to worry, we will try to be close to water with our topics. The first thing you need to know is the definition of outlier. So, to begin with, what's an outlier? Just to give you a brief and silly example of what an outlier is, imagine taking notes over the temperature in the Sahara Desert between January and February. Your notes will always point out that during the day, the temperatures get as hot as hell, and in the nights, it kind of cools down. But what happens if one of those days there's a rain that could be easily mistaken by a storm? That would be extremely odd, right? Well, that's one example of an outlier, because in that specific day, the temperature behavior wasn't expected. And most importantly, it didn't follow the temperature's data behavior. So, in a more mathematical language, an outlier is that observation whose value is separated enough from the normal population's behavior that can be considered rare or extreme. An outlier can be easily seen through almost every graph, but there are even easier to see in box plots. It will depend on the book or the professor, but you can say an observation is a suspected outlier if that observation is at a distance from 1.5 interquarter range or above. Here we have an example. As you can see in the graph, data's behavior relies on values between 0 and 1000. But there's another value included in the dataset that is not common or frequent, and whose value is far from the data's conglomeration. Both graphics are explicit enough to tell who the outlier is just by looking at them. And here you can see. So, as you can see, it is super easy and super intuitive to see what the outlier is just by looking at the graphs, right? So in this histogram that is below under the box plot, you can see the data values and different. I don't know what the data set is about, but I mean it's just to give you an idea. So you can see that it kind of like can be seen at the most of the values are between 0 and 1000, and that it looks like kind of like a normal distribution, but we cannot know, right? But the interesting point here is that later on in the graph, right after the 1000 value, there is some values that are that their measures are 1500. But those values do not behave like most of the graph, because the graph conglomeration relies between 0 and 1000, just like I said, and it is easier to see that those values that are 1500, it is not the right word to say it. It is not the right word to say it, but kind of like doesn't belong to normal behavior of the graph. And in the graph and the box plot above the histogram, you can see that there's the distribution of the same dataset, but shown as a box plot. And right there's a point. That point stands for the values which are 1500. And it is easier to see that does not belong to that box plot, that are not in the box plot, that are right after the third the last interquartile range. So these are ways to see what an outlier is. And to sum up and just to move forward, an outlier is that value whose did not follow or behaves like most of the data's values. As you can imagine, in data science, just like in any other science and in any other place in my life and everything, things are not as easy as you thought. So there's another thing you need to know about outliers before you can say that you know what an outlier is. So the thing that you need to know is that there's some classification of outliers, and these classifications can be easily described and understood. And once again, these classifications and descriptions of each one of these types are slightly different from book by book, but the general idea is that there are three types of outliers, and their classification relies on the meaning of the observation related to the data's semantic. These are the three types of outliers. The global ones. Global outliers are those observations whose values are distinct from all the observations previously seen. Let's give you an example so this can be fully and deeper understood, right? So, for example, if you are walking down the street taking notes on the things you see and you suddenly see a flying car, that will be a global outlier because it is extremely odd to see a flying car, right? So it is not usual in my city, neither any place in the world by now. So the next type of outliers are the contextual ones. If an observation's value is too far from the normal behavior of the dataset under the same condition of the observations, then you can consider that observation as a contextual outlier. Sounds like a tongue twister, right? Let me give you an example. So imagine, just as the previous example, that you were walking and then suddenly you see a tiger. Is that odd? Maybe. What about if you were walking in a zoo? In that case, that wouldn't be an outlier because I don't know where you live in, but at least in my country there's no it is not odd to see a tiger in a zoo. And I think in most of the places it is not odd to see a tiger in the zoo. At least that you're, I don't know. It is not odd. Let's keep it that way. So yeah, if you were walking in the zoo, in that case that wouldn't be an outlier. For contextual outliers, the only thing you need to understand, as the name goes, is the context in order to see if that observation was really an outlier. And finally, we have the collective outliers. These are way easier to detect. Collective outliers are those observations that do not follow the common behavior of the dataset, but that are not isolated. These are more than one outlier with the same characteristics. In that very same example as before, it would be like if you were strolling around the zoo and then suddenly a stampede takes place. Having a fugitive animal, it is not common at all, but having a lot of fugitive animals, that's a collective outliers. And I like to think about an example that I read in towardsdatascience.com. It was that goes like, what about if you live in a big department place, and kind of like a hotel, and your neighbor moves to another apartment? That would be odd. That would be on general outlier, because people tend to live in the same place for years and years and years, and suddenly a neighbor appears, moves. That will be an outlier because it is not typical. But what about if that a place wasn't like a department place but a hotel? Having different people in a hotel is not odd. Why? Because people that goes to hotels to Cancun tends to stay in there for a few days, a few weeks maybe, but then they move. They go to their places, they go back to their cities, to their countries, right? So that's a contextual outlier. But what about if you live in an apartment place and then suddenly all of your neighbors of the same floor as you moves. That will be odd, and that will be more than one case that is not isolated. So that will be collective outliers. And I like this example because it is easier to understand than mine, but I wanted to create one, right? So now that we have understood a little bit more about outliers, we are finally able to talk about how can we detect outliers using a very sophisticated method called proximity based, which is the main purpose of the video. And as you can see, I've already talked for, I don't know, 10 minutes, 8 minutes, but this was just for you to understand my words when I talk about outliers, and maybe you didn't know what an outlier is. So I just want my video to be as clear as possible. So here we go, proximity based methods. So proximity based methods, and just by reading and hearing the name, you can already grasp an idea of what proximity based outlier find method is. And as the name suggests, it is all related with the distance there are between one observation or more and the rest of the group. An outlier will be considered as such if the closest neighborhoods of that observation are at a significant distance away. If the proximity of the observed object is significantly away from the proximity of all other observed objects in the same dataset, then you can say your observation does not behave like the expected behavior of the majority does. Thus, it might be an outlier. And yeah, it again sounds like a tongue twister, but it gets worse, trust me. And as you can imagine, things are not as simple as they sound. There are 3 types of approaches you can take under consideration when you want to use the proximity based method. Well, in fact, there are a lot of algorithms that you can find on Google and toward data science, but we're just going to focus on 3 of those because we want to keep this video short. And I don't want to take a lot of hours doing the edition of the video because I'm not an edition magician, right? And you can already tell that by looking at the video. But let's moving forward. So yeah, the interesting thing in here is that all of the approaches are intuitive by the names. So here we go, the most important algorithms. The first one is called density-based approach. Density-based approach method is focused on density distribution of data points within a dataset. This method compares the density of each one of the observations with its local neighborhood's density, so you can give the observations an outlier score. Yeah, this approach does have like a huge formula to calculate the density, and you can also have a threshold to determine if the outlier score is high enough or low enough to be considered an outlier or a normal observation point. So here we have the formula, and let's move to the next algorithm, which is called the distance-based approach. This approach is the most common one to see, and as we just find out, the most accepted one as well. This method relies a little bit under the researcher or programmer criteria because he or she will need to determine a threshold so you can name some data as an outlier. The usual steps you need to follow for this approach are: first, you need to measure the distance from one point to another in the dataset. The second one is establish a threshold which is going to work as guide so you can tell whether the data is an outlier or not. You can find online a lot of metrics for you to determine your threshold. But in data science, the most common ones are the Manhattan distance, the Euclidean distance, and the Manhattan distance. I'm sorry for my pronunciation of those algorithms. And finally, you need to check whether your distance was under your threshold or not. Depending on the result, you will be able to tell if your result was or not an outlier. So, if you're keen on the data science world, or you like to read or do machine learning stuff, your algorithm will probably this algorithm will probably ring some bells later on in your professional life. It is very commonly used in data mining and some machine learning techniques that requires. So this algorithm is very well seen in the data science world and the machine learning world. So keep an eye on this one. As conventionalism, the K-means algorithm is the most used on this approach. In essence, it follows the same idea. The K-means algorithm uses an Euclidean distance as threshold. And just to continue with the idea, an Euclidean distance is, in a way, the straight line distance between two observations in an Euclidean space. The formula for doing this kind of metric is very similar as one you used in high school to find the distance between 2 points in a Cartesian plane, because in essence, and I'm going to read a lot of hate comments of mathematicians, but in essence, it kind of is like the same idea to find distance between points in a plane. So here you have the formula. We are going to, or at least I'm going to just one more time. I'm trying to explain you this formula because our main goal was to give you a theoretical explanation of this method. So let's move forward. If you have any doubt about the formula or about the usage of this formula, just do not hesitate on writing comments, and we will read them and we'll do our best in order to answer them. And maybe by now you can have an idea of how difficult it will be to measure distance between categorical data, and yes, it is. That's why nobody likes categorical data. So, to move forward, just consider the object in a figure that should be showing in the screen. So here you have. If we model the proximity of an object using its 3 nearest neighborhoods, then the objects in the region R are substantially different from the other objects in the dataset. For the 2 objects in R, their second and third nearest neighbor are dramatically more remote than those of any other objects. Therefore, we can label the object in R as outlier based on proximity. I mean, this everything relies on the distance. It is, well, the coding and the math could be difficult, but in essence it is easy to understand, or at least that's what I think or what I thought. The effectiveness of proximity-based methods relies heavily on the proximity or distance measure used. In some applications, such measures cannot be easily obtained. Moreover, proximity-based methods often have difficulty in detecting a group of outliers if the outliers are close to one to another. So yeah, and as I explained before, we could have multiple outliers that will be called collective outliers. Sorry, I forgot the word for an instance for a few minutes. But you can have a bunch of outliers with the same behaviors. So with given that they have the same behaviors and characteristics, their distance between outliers wouldn't be or shouldn't be as as big as the difference for the number of points. So from proximity-based method, outliers near the outliers will be detecting themselves as normal behavior, and that could be very tricky and difficult to handle. So yeah, whatever. The applications. Outlier detection is important in many applications, and just to give you a list of examples on instructions in communication networks, in fraud in financial data, fake news and misinformation, healthcare analysis, industry damage detections, security, and so on. Just to give you an idea or picture, I remember our teacher in class told us about a very good example of the usage and the importance of outliers in the fraud and financial data. He explained that what about if you have a credit card that hasn't been used in a while, and then suddenly you decide to, I don't know, to buy, what can you buy with a credit card? I don't know, a house. Let's pretend that you can buy a house with a credit card. And yeah, that will be extremely odd because you usually don't spend a penny. So if the bank detects that from zero you pass from zero to spend $1 million, that will be extremely odd, and the bank can froze your account because they might thought that that's not you, because that's not how you behave. That will be an outlier for them, and hence they will be dealing with outliers as it. This could be very important. Maybe your credit card got stolen and somebody bought something that you usually do not buy, and the bank can't help. So it is extremely important to detect and to work with outliers.
Now we will see an example of the application of the local outlier factor algorithm, with its acronym LOF, from the data.csv. So, dataset based on the frequency of click in a series of videos. For this, we will use the libraries pandas as PD, NumPy as NP, Seaborn as S and S. And from CPy, we will use the bdist square form. First, we need to open our CSV with the read SSV. Then we use the head to can view the data. So we create the reach this function, which will return the value of the data frame entered in the desired position. Then we create the LOF algorithm function, and then by means of the bdist function, we calculate the distances with the CTBlock metric over here. Once we calculate, we generate the distance matrix by applying the square form function, which converts a vector into a square matrix. Once the matrix is obtained, we add a data frame over here. The following conditions determine of the value of k. We create some dictionaries that we will use later. We create these dictionaries and then we will storage our data. And we will begin a cycle with which we will determine the distances, the key neighbors, for each element in the observation list. After determining the distances, we will insert in another cycle. Over here for index, and in this cycle we determine the distances between its observables and its indexes. Then we will select the neighboring k from the selection of the .ns smallest function over here. after calculating the other variables, we add the value of the reach distance list variable to the reach depth array list. Then over here, first we create a dictionary, an empty dictionary to store our data. We create a circle for observation. In observations, we iterate in each value of observation, and then we calculate the log using the formula described in the documentation. Finally, the top 5 distances return, which are anomalies. Over here, in the first function, we have the same inputs, and we define P as 5, which is the number of outputs that will return. And by default, distances metric is city_blocks. We cannot see this, but in the next example we can see it. Over here, in this example, the distance metric is Euclidean. This concept is described above.
And as you can see, after applying the method we explained so far in this video, we found the outliers and now we are ready to keep working on the dataset. Thank you so much for your attention. Hope to see you around soon. And as I said before, do not hesitate on asking or commenting if you have any doubt. Yep. Do not forget to subscribe as well. We want to drop out of school and become YouTubers. So help us achieving our goals. See you later.